Hello everyone. So today we're going to continue on 7.4. So if I remember correctly, in the last three videos we get to talk about change of variable, but for only for the three coordinate system that we already know, which they are polar in R2 or spherical or cylindrical in R3. And one of the biggest things that we need to figure out when we do that is that we have to change three things. The integrand, which is basically doing a composition using the transformation. The regions of integration, which we kind of have to find the corresponding regions in the new coordinates. But most importantly is to find out how the differential are related. And so far we noticed that in the polar, dx dy would actually equal to r dr d theta. There's a scalar r that kind of scale between the differential. And then the spherical coordinate system, dx dy dz would actually equal to r squared sine phi dr d phi d theta. So once again have something r squared d sine phi, which is there to kind of correspond the two differential together. And then the cylindrical dx dy dz become r dr d theta dz. So there's an r there that kind of show the relationship between the differential. The problem is that we haven't really talked about how to come up with that. And there are some geometrical ways to figure that out. But of course, sometimes it's hard to draw them in whatever dimension that's in, and not to mention geometrically, we can calculate it, but probably only in the dimension that we can actually visualize the geometry of it. So we need a more algebraic way to do it, and that is introduced by the Jacobi theorem. So the theorem is stated on page 342. So in case if you have anything unclear about it, you can go ahead and go back to there to figure it out. So imagine the following, okay, based on this theorem. Imagine the following. Let's say we're given a coordinate transformation T in Rn. We don't know what this transformation is. It could be anything, as long as it's a coordinate transformation. That means it has to satisfy the condition needed for a coordinate transformation. But let's say we have this coordinate transformation. And let's say this coordinate transformation basically will transform a subset of Rn, which we're going to call Un, onto Rn. So therefore imply that T with a domain of U sub n, U to the n, and it will map into Rn. And we're assuming that this coordinate transformation is 1-to-1, has an inverse, and it's mapped into pretty much the entire Rn. Maybe with some few exceptions, but we would pretty much assume that it will map into the entire Rn. And we're going to define this function to be T of vector U equal to vector x. So therefore, the input is basically what the vector U is, and the output would be the vector x in the Rn coordinate system. So in another word, in this picture right here, vector U is like r theta, or r theta phi, or r theta z, and then vector x would be our typical xy or xyz, or and things like that. Okay, and let's say this coordinate transformation is continuously differentiable, so which means that we want it to have a derivative. And we're going to define two regions R. Let's say let R be a region in the domain of this transformation with its image T of R in Rn. So once again, it's basically talking about like regions R is in the polar coordinates and T of R would be in the XY coordinate system. So if you want to make a note for yourself, you should. So here U to the N is basically our curvilinear coordinate transformation, while Rn is our typical rectangular coordinate coordinate system. So what does Jacobian theorem state? The Jacobian theorem basically states the following. Once you have all this set up, then if we take the integral of the regions T of R, which is in Rn, the function f of vector x, because vector x is in Rn, because that's in the output of the transformation, dv in the vector x dimension, so in this case dv is basically d vector x, kinda, okay, this integral can be rewritten into the coordinate system vector u using this formula. It will be integral over r, because r is in the u to the n, which is the domain of the transformation, f of t of vector u. So notice you basically put the transformation inside to form a composition, just like how we normally would do it. Here's the important part. Multiplied by the absolute value of the determinant of t prime. Multiplied by dv in the vector u coordinate system. So once again, there's a lot of things going on here that I need you to kind of think about and understand. So in here, T of R is basically the regions given in like the XYZ coordinate, and R would be the region in the polar coordinate or cylindrical coordinate system or the spherical coordinate system. Okay? And dv in vector x is basically just mean dx dy dz or dx dy in the case of dx dy dz, or in the case of the polar would be dx dy. Okay, so that's what dv vector u is, vector x is. And dv of vector u right here will basically just be like dr dz, dr d theta dz, okay, or dr d phi d theta. Okay, so they are just basically between the two coordinate system. And here, the way you remember vector x is the xyz coordinate system, just like what we always use vector x to represent, xyz. So here's the interesting thing, is this part right here. That is actually where the r come from polar, or the r squared psi phi came from. So in this formula right here, the important part is dv in the xyz coordinates is actually equal to this absolute value of the determinant of t prime times dv vector u. So this basically formed the scaling factor that we've been looking for. And because of that, this thing right here has a special name, so let's talk about it. So in here, remember that t is the coordinate transformation. And T prime would be the derivative matrix of the coordinate transformation. And you learned that in 6.5 that it has a name. So T prime is the Jacobian matrix. Then what is the determinant of T prime? That is called the Jacobian determinant. which is basically the determinant of the coordinate transformation derivative matrix. Now, interesting thing to make sure you pick a note for yourself is that this determinant can be positive, can be negative. We only want the positive of it, okay? We don't want it to be negative. Some of you may ask the question, then what does it mean when it's negative? See, this determinant actually forms the scaling factor between the regions before and after the transformation, the scaling factor between the volume or the content. If it is negative, it would indicate that not only that has the proper scale, but also reverse the orientation of the regions. But since we don't really care about the orientation, we don't need the negative, which is the reason why we have the absolute value there. Now, it might sound very confusing, but how about show you how that is relating to the polar coordinate and the spherical coordinate system and things like that. So here's a very simple example. Let's say we let t of r theta equal to r cosine theta, r sine theta, which is equal to xy, be the polar coordinate transformation. So essentially, this is my vector u, this is my vector x. That's basically what it is. Okay? What I'm going to ask you to do is, I'm going to ask you to go and try to find its Jacobian determinant. And if you are thinking about it, you should know what the Jacobian determinant is already, because based on this expression right here, this one right here, and now look at the polar coordinates. You recognize that that's what the r is supposed to be. So that would mean that the Jacobian determinant for the polar coordinates should equal to r, because that's how you relate the two differential together. So let's see if that's the case. So here's what t is. Oops. T of r theta is equal to r cosine theta, r sine theta. So you can definitely just form the derivative matrix. Or you can look up in 6.5 because we did all the Jacobian matrix for all the coordinate transformation that we did. But it shouldn't be too hard to figure out. So that would be cosine theta and negative r sine theta. That would be with dr and then d theta. And then for bottom will be sine theta. And that will be r cosine theta. So that would be my Jacobian matrix. So now to find the Jacobian determinant, that just basically equal to determinant of t prime. So that just basically means the determinant of cosine theta negative r sine theta r cosine theta. Oops. So what's the determinant of this 2 by 2 matrix? So remember, there will be AD minus BC, so therefore become cosine theta times R cosine theta minus sine theta, oops, times negative R sine theta. So what that come out to be? Well, that come out to be R cosine square theta plus r sine square theta, where we factor in r. And when I do that, I will have cosine square theta plus sine square theta, which we know that turn into 1. So that would just become r times 1 or just r. There you go. So that is basically what the Jacobian determinant is. So this is basically what the determinant of t prime is equal to r. So now I can say that dx dy, dx dy is actually the absolute value of the determinant of the Jacobian determinant times dr d theta. So therefore become this formula, which is basically the formula that we already know when I first introduced to you the formula for polar coordinate transformation. Now, it's probably interesting to see what is the spiritual one, so let's go and do that one too. So let's say that we let t to be r phi theta, and that's equal to r sine phi cosine theta, r sine phi, sine theta, r cosine phi. I'm going to try to find the Jacobian determinant for this coordinate transformation. All right, so let's go and do that. So what I need to do is find the Jacobian matrix first. So that will be t prime of r phi theta. So it's not too hard to figure out what this is. If you simply just differentiate, you should be able to handle that. That will be psi phi cosine theta. And then differentiate with phi would be r cosine phi cosine theta. Differentiate with theta will be r sine phi times negative sine theta. So I'm going to put the negative in front. Second coordinate function, if I differentiate with respect to r, it will be psi phi sine theta. Differentiate with respect to phi would be r cosine phi sine theta. Differentiate with theta will become r sine phi cosine theta. Differentiate last one with r will be cosine phi. With phi, it would be negative r sine phi. And then with theta, it would just be 0 because it doesn't have a theta in it. So now what I need to do is try to figure out what is the determinant of this thing. Now notice that this one is a 3 by 3 determinant. So hopefully you remember how to calculate that back in chapter 2. So one way to do that is to just use the top row and just do minor matrix. And I can totally do that. I guess we could probably just do that. Let me just do that. Okay. So what is the determinant of t prime of r phi theta? So that will actually come out to be the following. So remember is basically sine phi cosine theta multiplied by the determinant of r cosine theta sine phi r sine phi cosine theta negative r sine phi 0. And then is alternating signs, so I'm going to subtract r cosine phi cosine theta multiplied by the determinant of sine phi sine theta r sine phi cosine theta cosine theta 0. And then plus the last term is negative r sine, so I actually wind up being minus also. Oops. And then multiply by the determinant of sine phi cosine sine phi sine theta theta, and then r cosine phi sine theta cosine, oops, that's a phi, not a theta, and then negative r sine phi. So now just a matter of trying to figure out what all of these come down to. So let's give it a try. So this would equal to sine phi cosine theta. The determinant of this 2 by 2 matrix will first be the a times d will be 0 because you have d equal to 0 minus b times c. So here become actually multiplied by minus, so become plus. So become plus r sine square phi cosine theta minus r cosine phi cosine theta multiplied by the determinant of this matrix. So same thing, because d is 0, a times d would be just 0. And then you have negative r sine phi cosine theta. And then minus again r sine phi cosine theta multiplied by the determinant of this thing, which actually come out to be have 4 terms, because like you don't have the 0 anymore. So here become negative r sine phi square sine theta minus r cosine phi sine theta. So that's definitely not that pretty to look at. But you know what? Look can be deceiving. So let's try to clean this up. So let's see what I can do if I try to clean this up. Okay. Let's see. All right. Oh, actually, I noticed a mistake. This will be negative r square sine square phi. So that's a square. So now if I multiply this out, that should be r square sine to the third phi cosine square theta. If I multiply this out, it becomes minus r square, or actually plus, because it's minus a negative. And then let me see, I'll have sine phi cosine square theta, cosine square phi cosine square theta. And then now let's do the last 2 terms. So this would actually negative times negative become plus r square sine to the third phi sine theta square theta plus r square sine phi cosine phi sine square theta. All right. All right, so let's see what we can clean up. So I'm looking at this right here, and I noticed the following. If I look at these 2 terms, okay, if I look at these 2 terms, wait, let me see. Okay, all right. Yep. Actually, I noticed another mistake. I'm missing a square here, because it's cosine phi times r cosine phi sine phi. So therefore, I'm missing a square here also. Now that makes more sense. So now let's see. So if I look at these 2 terms together, I can actually factor out r squared sine to the third phi, and then I will have cosine square theta plus sine square theta. If I look at these last 2 terms right here, these 2 terms, notice I could factor out r squared sine phi from them. And what I have would be, actually I can also factor out cosine square phi. So cosine square phi, oops, wrong letter. And then I would have cosine square theta plus sine square theta. So we know that come out to be 1, and that come out to be 1. So therefore just become r squared sine to the third phi plus r squared sine phi cosine square phi. And if I now factor out r squared sine phi, I will have sine square phi plus cosine square phi, which that also come out to be 1, and that come out to be this. Now, is that shocking to have that as an answer? No, I mean, that should be exactly what the answer is, because in this case, if you think about it, it makes sense, because this is basically what it's saying. For this coordinate transformation, dx dy, dy dz would equal to the absolute value of the determinant of t prime times dr d phi d theta. And we just found out that that determinant is right here. So therefore, give us this relationship. Now, one thing some of you who keen-eyed may notice the following is that I actually don't have the absolute value around this, nor did I put an absolute value around this one when we did it. So what's up with that? Well, the problem is the following. For polar coordinate, r is defined to be only a positive value number because the domain for r is 0 to positive infinity. So therefore, the absolute value will go away because r is already positive. Okay, makes sense? For this one, then why did I drop the absolute value also? Well, because r squared is automatically a positive number. Sine phi is also a positive number because we are only consider phi to go from 0 to pi, which is quadrant 1 and quadrant 2, which we know the sine of any angle in quadrant 1 and quadrant 2 are always positive. And therefore, that's the reason why we don't need this. Now, I would like you to go ahead and try to do the Jacobian determinant for the cylindrical coordinate system. And that way you see that why the cylindrical coordinate system come out to be whatever it is from the formula. But that's basically what this thing that I've been telling you to remember when you do your change of variable, but I haven't been able to tell you how that come about. Now you know where it came from. It's actually come from the Jacobian determinant, the absolute value of the Jacobian determinant, which is basically just the absolute value of the determinant of the derivative matrix of a coordinate transformation. All right, so I think I will stop right here so that my video is not going to be too long. We will get into some example using Jacobian theorem in our next video. All right, I'll talk to you guys next time. Bye-bye.